afternoon, Professor. This is Brian Coffin. This is the Mod 2 lab. Finally getting caught up on. To start with, we're going to do the brief overview of the safety precautions. To start with, add my fire extinguisher, paper towels, and also I use the stainless steel plate on top of the countertop at the sink. Around that door over there is the bathroom with the sink and shower in it. Also, I used my safety glasses and gloves for the experiment for the lab. I believe that's about it for the safety aspect of it. We'll get into the results here. Going with table 2, the observations. I'm going to turn this around somehow. Well, maybe I can't. I don't know. Anyways, the observations. The lithium chloride was, once I did that experiment, when you put it in the flame, a lot of popping and cracking noise in the flame. It's about all I noticed. When it comes down to the sodium chloride, the observation was the same. There's a lot of popping and cracking noise coming from the flame. Potassium chloride, flame didn't really do anything like the popping and cracking noises of the previous two. One thing I did notice, the liquid in the loop looked like it was trying to solidify as it burned off. The calcium chloride popping and crackling again, and had actual looked like small sparks popping out of the flame. It actually looked like fireworks. Table 3, the electron configuration. Well, for the first one, it's already got it. The second one, Li, was 1s2, 2s1. Na was 1s2, 2s2, 2p6, 3s1. Ca was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now we'll go to the color, the light emitted by the salt types. The lithium chloride looked like to me it had a reddish tint to it, the flame. And the wavelength, I figured it at 680 nanometers. The sodium chloride, I believe, had what it looked like to me was yellow, and I figured that one at 615 nanometers. The potassium chloride was kind of a faint purple. The wavelength I figured at 430 nanometers. The calcium chloride looked orange, whether it didn't change or the flame was just staying orange. I figured that one at the wavelength at 640 nanometers. To the next, we'll go with for the self-reflection. Did I turn to a particular resource to supplement my knowledge as I progressed, and what was most helpful and least helpful? For the electronic configuration, I didn't have any problems with that. The one thing I did have problems with, and I had to refer to the book, was the wavelength. I had to refer to Chapter 7, Section 7.2 for help on the wavelength, so I could figure out how to come up with a wavelength on its own. So didn't really find anything that was least helpful. So we'll move on to the Section 3, critical thinking. Underlying chemistry principles applicable in both the flame test and atomic emission spectrum. I put, I wrote something down real quick. The atomic emission spectra are created when atoms of an element have energy added to them by heating or running electric current. With the naked eye, you see a single color of light, which is, the sum total of all colors, light produced by a given element. Another thing I said, a spectroscope will reveal the unique frequencies of light being given off by atoms of the element. So that's my answer for that. Next would be explain the process of writing the electron configuration. It's pretty much the same thing for all of them, but I'll just do the lithium to start with. Lithium is the third element with a total of 3 electrons. When you write the electron configuration for lithium, the first 2 electrons will go with the 1s orbital. Now, since 1s can only hold 2 electrons, the remaining electron for Li go to the 2s orbital. Therefore, the Li electron configuration will be 1s, 2, 2s1. This is basically the same. Well, it's not basically the same. It is the same for the other 3. When it comes down to figuring them, we'll cover them really, really quick because I know I'm running high on time. 1s can hold 2 electrons. The next 2 electrons for sodium go to 2s orbital. The next 6 electrons will go to the 2p. The p orbital can hold up to 6. We'll put 6 in the 2p orbital, then the remaining electrons in the 3s, so you get 1s2, 2s2, 2p6, 3s1. Then for the calcium, it's a little bit longer of 1. Same thing applies. 1s can hold 2. The next 2 electrons for calcium go in the 2s orbital. The next 6 will go in the 2p. And again, it can hold up to, the p can hold up to 6. Then we put the next 2 electrons in the 3s. Since the 3s has all it can handle, we'll move to the 3p where the next 6 electrons will be placed, and then you go to the 4s orbital where we replace the remaining 2 electrons. And the electronic configuration for calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. All right, that's the end of this lab and this post-lab video. I hope I covered everything, and I hope I did everything right to your satisfaction. Thank you.